Hello everyone, welcome to today's lecture. Today we are going to talk about basics of programming. But we are not yet going to do any programming in this lecture. We are rather going to talk about some terminology first. For example, what is programming, what are programming languages, what is syntax, semantics, etc. And then we are going to take a quick look on the today's programming languages and see how they are divided to different groups. For example, how they differ in the level of abstraction and how their execution is on your machine or on your computer. And then we are going to talk about different phases of programming, because programming is not just about opening a text file and start writing your program. There are several steps that are needed to be taken beforehand and some steps to do afterwards. So let's start here. What's programming? A computer is a hardware machine. A hardware are those physical parts of a computer that we can see and touch. Computer is a hardware machine that can store and process information, as we have seen in the second lecture, that how transistors are used to store information and how logic gates are used to process information and do different sorts of computations. Programming is actually the process of developing a program that acts according to our wishes. We want to write a program that does what we intend to do. What is a programming language then? It is simply a language to communicate with your computer, and it has some similarities to human languages. For example, it has a set of vocabulary that are fixed, and it has some rules that we need to use. What is a program? It's simply an organized collection of instructions to perform a specific task. So a program, it translates the programmer solution for a problem, for example, for doing some arithmetic operation, etc. It translates that into a language that can be processed by a computer, because we cannot nowadays simply just intend something and imagine that the computer would do it. We need to translate it to translate our intention to something that computer understands. But what is the language that the computer understands? If we go back to the previous lecture, we remember that the computer understands or is built of transistors, logic gates, logic circuits, etc. So those elements are the things that the computer understands, and the binary digits, etc., are things that are known to computers. Each computer has a special architecture, meaning that its CPU is built in a certain way. Its buses that move the data and instructions are performing in a certain way. Its memory is addressed in a certain way. All these are called architecture, and they are specific to any computer, any processor that is in the market. For example, Intel has several processors, and each of them has a specific architecture for its own. Computer understands a so-called machine language. Machine language is a collection of bits that the computer reads and interprets. Because, we discussed about bits and transistors, and we saw that a bit can be represented by a transistor. And the language of bits is something that a computer understands. And for any specific architecture, there is a specific machine language, which tells, for example, what is the specific number assigned for each instruction. Because when we work with computers, everything is translated into different numbers. We saw, for example, how characters are translated in terms of numbers in the ASCII standard. There are also other numbers associated to different instructions that you want to do in a computer. For example, when you want to use addition, there is a specific command for that, which has special number assigned to it. And when you want to read some data, there is a specific number assigned to reading and writing, and storing is the same as writing, and so on and so forth. So the locations, the memory locations on a computer are also formed in terms of numbers which show the address of each part of memory. So this comes with many details. I mean, machine language comes with many details, many zeros and ones, etc., etc. So one way is to actually write our program in terms of a machine language. But machine language depends on the architecture, as I said. So for every computer, its machine language is different. And you can imagine it can be very hectic to learn and use a machine language. You can see in this picture a sample program written in some machine language. You see it's not readable at all. We see just some hexadecimal values here that are maybe some instructions and followed by some other values. It is not readable at all for us humans. So doing programming in this language needs a really expert person that knows all the details about the hardware and about the architecture of the machine. It's not doable for other people. Another kind of language that is used for programming is called assembly language. Assembly language is a symbolic representation of the machine code or machine language. I will choose machine code and machine language interchangeably. So there is basically an assembly language for a specific machine language. So again, assembly languages depend on the architecture of the computer. But since assembly language is a bit symbolic, meaning that it doesn't have all those details of zeros and ones and numbers, sometimes it has some words that are readable for us humans. Because it is in a different abstraction level, it is translated to machine code in order to be executed on a computer. And the program that does this translation is called an assembler. So you can see here in this picture an example of an assembly program. This program, what it does, it seems like a long program, but what it does is that at the end it prints hello world. Printing hello world is classic. Whenever you want to start a new programming language, it is classic that you write try to make your program, your first program, print hello world. This is simply what this program is doing. So you see here, we don't have only numbers. We have some instructions that maybe we can guess what they mean. For example, stop I here means that there is maybe some subtraction going on here, or here we are supposed to have some sort of looping, and so on and so forth. So it's much easier to learn what this program means. We can just simply learn what these special names and keywords mean, and then they can follow to some extent the instructions that are here. So you see here a program, they said, is a set of instructions that are going to be executed by the computer. So see how long this is. For just doing a simple task, it just wants to print a fixed sentence on the screen. It's not going to ask any input from the user. It's not going to calculate anything. So let's see what other programming languages can we have to communicate with the computer. So here we see a sample of a high-level language. When we say high-level languages, we mean that they get closer to English, and they get the distance from the zeros and ones that the computer understands. But there is no magic happening here. When we want to talk with the computer and give it instructions, we need the computer to understand what we are saying. So whenever we write a program in a high-level language, that program needs to be translated again by some underlying program to the language that computer understands. But it gives us many opportunities. For example, the programming gets easier with these high-level languages, and more people can program. If only technicians and computer experts could program with machine language, now with high-level languages, sometimes even school kids can program as well. So here you see a program written in Python, which is printing hello world, and you see that this program is just one line of code. Compare it to the assembly version. The machine code version would be much longer even than the assembly. So this is much easier, I guess, to learn this language rather than machine code and assembly language. And this is why programming is getting more and more popular nowadays. So let's look at this picture. Here we see different levels of programming languages. And by different levels, we mean level of abstraction, which essentially means how do we abstract away the details of the architecture of the program. So at the bottom, you see we have the hardware, which is built of switches and gates, etc. And the language that directly works with hardware is machine language, as we already discussed. So it has too much details. It completely depends on the architecture. And the next level, we have assembly language, which hides some of the details from us. For example, in assembly language, we can have the store and subtract and add instructions, but we don't know, or we don't need to know what is the actual instruction in terms of zeros and ones when it comes to the hardware. So it abstracts away some of the details for us. And on top of an assembly language, we have high-level languages such as C, C++, .NET, C#, etc. And on a higher level, we have Python, Java, JavaScript, etc. And at the topmost, we have here, as you see, Scratch and App Inventor. So nowadays, school kids can do some extent of programming with Scratch, but in the old times when only machine language was used, only experts could do it. And this kind of programming was sometimes done with punch cards, with switches, as we saw in the first lecture in computer history. So it wasn't even done by writing simply in a file, because these files that we're working nowadays with didn't exist back then. So as we go up in the level of abstraction, the programming gets easier, and in Python already we are independent of the underlying architecture, meaning that whenever we are programming, we don't care at all about the CPU, about the buses, about the memory details, memory addresses, etc. We just write our instructions, and there is some sort of translation done underneath until it arrives here. But when we come down, the details are added and we get closer to the hardware of the computer. So one way to cluster programming languages is based on their abstraction level. The other way is to compare the programming languages from this perspective, that whether or not they are compiled or interpreted. What does it mean? Let's review again. A computer thinks it's in binary because it is built of transistors and gates, etc. When we have a high-level program, it needs to be translated in a language that computer understands. Compilers and interpreters take the high-level languages, which are written in human-readable code, and translate it to computer-readable code. So in compiled languages, we have a program called the compiler. You might have heard this word used often. A compiler does this. So it takes the entire program. This is important. It takes the entire program that you have written and translates it to machine code. So, we can only program in high-level languages as long as we have these translators, being compiler or interpreter. So when a compiler compiles our code and transfers it to some sort of machine code, it actually does on the machine code some sort of optimization, because compilers can detect, for example, if some parts of our code are redundant or are useless, meaning that they don't contribute to the computations that we have, so they remove them, and they do many different things to make our code optimized, meaning that the machine code that they produce at the end usually runs faster compared to interpreted languages, because the compiler tries to optimize the code. But in interpreted languages, we have an interpreter program. You can think of an interpreter program like an interpreter when two people are talking to each other with different languages. So the interpreter should listen to sentences one after another and translate it to the other language. The interpreter does something similar. It interprets the program instructions line by line or instruction by instruction, and converts them then to machine code. So it doesn't need to have the whole program at once. It just executes the instructions one by one. It has some advantages and disadvantages. One of the advantages is that it cannot do the optimization that a compiler can do. A compiler can do the optimization because it has the whole picture, it has the whole program. So it can see what instruction is needed, which one is not needed, which kind of memories can be saved, what things can be combined together. We are not going to go to details there, but it can do make the code work faster. But the interpreter cannot do that. So the code the interpreter produces is usually a bit slower than the code that the compiler produces. But the advantage with interpreted languages is that since it just reads your program instruction by instruction, you can change your program even if the interpreter is working. For example, imagine the interpreter is just reading the beginning of your program. You can do some modifications, some corrections to the later parts in your program before the interpreter reaches there. But in the compiler, you cannot do that. It takes your program as a whole. Once it starts compiling, whether or not you change your program, it will not affect the results. You need to run the compiler once more. Examples of interpreted languages are Python and JavaScript. We are going to talk about Python in this course in the next lecture, actually. So now that we have seen different levels of programming languages and different types of them, which is compiled and interpreted, let's go to the real programming and see how writing a program is done. Again, I'm not going to the details of any programming language yet. I just want to summarize all the steps and introduce to you some instructions that are used in almost any programming language, high-level programming language today. we will talk about the high-level programming in this lecture, but in a later lecture, we will talk also about assembly programming. But so far, what we say is just about high-level programming. High-level languages share many different concepts with each other. And as soon as you get acquainted with one high-level programming language, the process for you to learn another language gets much easier because you already know many terms and the logical idea behind programming and how should the programming task be done. So when we want to write a program, we don't just directly go to the programming language and start the so-called coding. What we need to start beforehand is to do some sort of analysis. Then we do our coding, and then we need to test our code, because otherwise our code cannot be executed. It's very unlikely that you can just write a code that directly works and gives you the expected result. Usually you need to have several iterations of testing and then correcting your code and again testing and correcting, etc., etc. So in the first phase, we do some sort of analysis. Let's see what it means. So we need to analyze the problem that we have. What is the problem? For example, imagine a very simple problem that you are given. You want to sum up you want to get as input two numbers and sum them up and print the results. So you need to think about what is your solution. When it comes to choosing a solution, we need to talk about algorithms. I will talk about it in a next slide, but then what you need to also think about at this point is that what are your inputs, what is your output, how you're going to get them. For example, are you going to ask the user to give you some inputs, or are you going to write your inputs in a file? How are you going to import those inputs into your computer, and what should the output be? Is it like a number? Is it a big file? How should it be represented or stored, etc., etc. So now let's talk about algorithms a little bit. Algorithm is a term that is named after the Iranian mathematician and physicist in the 9th century, who was called Muhammad al-Khwarizmi. In Latin language, al-Khwarizmi is said algorithmi, I think. So he was the first person to introduce decimal numbers and introduce the algorithm on doing arithmetic operations on those numbers, such as subtraction, addition, solving easy to difficult equations. But those algorithms or solutions were not called algorithms by then. This name was given later on, several centuries later, to algorithms. So nowadays, we use the term algorithm to mean a step-by-step procedure for solving a particular problem. Algorithms are actually something we might use every day. For example, consider a cooking recipe. It has step-by-step procedures, and usually you are supposed to follow this in the procedures in the order that they are written. You should not you should not usually change the order. So when we want to use the computers to solve our problem, we need to have and find the algorithm that we want to use. Algorithms are independent of programming languages. And algorithms are the way that you think about solution to the problems, the steps that need to be taken. And for a simple problem or difficult problem, there can be several algorithms. And for example, consider different solutions to a math problem or a different ways you can reach a certain address in the city. These algorithms can be different in terms of execution time, in terms of the amount of memory that they use, etc., etc. For example, consider sorting numbers. You are given like 10 numbers, you want to sort them from the smallest to the biggest. Sorting is actually something the computers very often do. When you want to sort n numbers, you can have an algorithm that needs n square instructions, but you can also have several algorithms that need n times log n instructions. They are discussed very much in computer science, that what are different sorting algorithms, what are different algorithms to find the maximum, let's make this algorithm more efficient, etc., etc. In this course, we are not going to go to too much details. We just want to know what are algorithms and how we can use them in our programming. So when we have a solution, we need to represent it in some way. There are usually two ways to represent the algorithms that we have in our mind. We either should choose flowcharts or we use pseudocode. Let's see what they are. Flowcharts is a diagrammatic representation of an algorithm. It's helpful for both writing programs and explaining the program to others. So they are diagrams. They show you where your program starts and what steps does it follow and what does it produce and so on and so forth. We will see some instructions and examples in the following slides. When we want to use flowcharts to represent our algorithms, we need to first learn the symbols that are used to show a flowchart. An arrow is used to show the flow of logic. For example, where we start, where do we go, and where do we end. It shows the direction. Ovals are used to show terminals. For example, where does the program start and where does it end? Those locations are shown with an oval. Parallelogram is used to show inputs and outputs. We put them in the places we want to ask for an input from the user, or we want to, for example, print out an output. Rectangles are used to show processing. For example, doing addition, subtraction, multiplication is put in these shapes. And finally, we use a diamond to show decision. For example, does something hold or not? Do we want to take this path or that path? In those places, we want to take a decision, so we use diamonds. Now let's see some sample flowcharts. So imagine we want to receive two numbers from the user and add them up. How should we represent our algorithm? So the algorithm in this case is very simple. Just read those numbers and add them together and print them. So first we need to have the terminals. Here we have the start and the stops, and you see with the arrows we show the flow of the program. This program is just very straightforward. It has just a very straight line as its as the flow of its logic. So first we need to declare variables. I will talk about it in the later in this lecture. So we need to declare variables, meaning that intuitively we need to assign a part of the memory to store those two values we want to get from the user, because they are going to be written to memory. So first we declare them and then we read those numbers. Imagine we have given the names N1 and N2 to them. Then we have, so here we have a parallelogram because we have an input instruction. Then we have a rectangle because we have some sort of processing, which in this case is that adding those two numbers together and storing them in a new variable. Here we call it sum. And then we have an output operation, which is displaying those numbers, which is shown here in this parallelogram. And after that, we are done. So our program terminates here. So we have the stop here. So this was very easy. It's basically for this easy algorithm, the flow chart is just as easy as you can think it in your mind. You just put them in the correct symbols for input, output, terminal, etc., and you connect them using the flow arrows. Let's see another example. In this example, we want to get 3 numbers from the user and we want to compute their maximum, or we want to find which one is the largest. So again, we need to have always the start and end. This is common to every program. And in the first, we declare variables or 3 variables, which we here call them A, B, and C. We'll see later on that each variable has a unique name and so that we can access them later on. It's like having variables in algebra and math. In the next step, we have an input operation, which is to read those input variables and or obtain them from the user. Here in this diamond, we want to check something with this. We want to check whether or not A is larger than B. We are going to check our numbers 2 by 2 so that at the end we come up with the largest number. So you see here, the flow of the program is can either be here in this branch or in the other branch, depending on the result of this comparison. So our program is not like the previous program, just a straight line. The flow of logic is not a straight line. We have some conditions which direct the flow in a specific direction. So if A is larger than B, then intuitively we don't need B because B cannot be maximum. It will be either A or C. So we continue in this branch and then we compare A and C. If A is larger than C, then A will be our maximum value. So we have a printing step, which is shown by this parallelogram. If A is not larger than C, we have false here. True and false, if you remember from the previous lecture, are Boolean values, which are used in programming a lot. So if A larger than B doesn't hold, so the result of this comparison is basically false because this is a false statement. A larger than C is a false statement. So we continue here and we are sure that our maximum value is C and we print it. And let's go back again here. If A larger than B is not true, so it is false. So which means that basically B is greater than or equal to B. So we continue here and then we don't need A anymore. We just need to compare B and C. And if B is larger, then we print B. So this program is also very similar, but you see, very simple, but you see that drawing its flow chart seems a bit tricky to come up with the decisions and inputs and outputs, but this basically shows what is your algorithm, what are the steps that you want to take towards solving the problem. So first you are saying I want to compare the first and second values. Then in the next step, I compare the result of the previous section with the third value, which was C, and so on and so forth, and you come up with maximum in any path. And then after this printing part, the program finishes, so we have the end symbol. So flowcharts are a way to give a graphical view of your solution, to see what are the branches, how does the logic flow, and where does the program start and end, etc., etc. But there are other ways also to show algorithms. One which is very common is called pseudocode. Pseudocode, as its name suggests, it's like a fake code. It's not a code in any programming language, but it is an informal language that is somewhat closer to how a programming language would look like. But it doesn't have any syntax. So syntax, we will talk about it later. Syntax are the rules that are specific to programming languages. For example, Java has its own syntax, which says how we should write our program. Python has another set of syntax rules. But in pseudocodes, you don't have any syntax. You just write as you think, something which is human readable, and everyone, even without knowledge of programming, can understand it, but it is in some way structured, similar to a programming language. We will see it in a few examples. And this kind of program that you write can certainly not be compiled because it doesn't respect any rule from any programming language. But what it does is that it gets you one step closer to the actual program that you want to write in a certain programming language. It makes you to decide what you want to do, to discuss your idea with others, because it's not always easy to just start programming. You need to get several steps to get more and more closer to the program that you want to have. So let's see how to write a pseudocode. So we need to think about the problem that we have and the solution that we have found, and write the solution in a sequence of tasks, like a recipe again. But now we don't have the symbols a flowchart has. No, we write it in a human readable form without any symbols. But it is good that when you write your pseudocode, you sometimes put an indentation at the beginning of your line to show dependency. For example, when you check some condition and you want to do a specific action based on that, the actions should be intended so that it shows that these actions depend on that condition. We will show it in some examples. And at the end, you should check your pseudocode. Does it involve all the steps that you had thought? Does it terminate? Because what is very important about the algorithms, about the solutions, is that they have to terminate. Otherwise, they are not called algorithms. Algorithm is a set of steps for a solution that will terminate. Otherwise, your program has some sort of problem, gets stuck somewhere and doesn't terminate. This is not good when you want to program, unless there is a very strong reason to do that. So now let's see some sample pseudocodes. So here we go back to the same problem for which we drew the flowchart, which was to find the largest among three different numbers. So let's see how its pseudocode would look like. So it will look like something like this. You see, it's human readable. It doesn't have any symbols, but it has some sequence of information, some sequence of instructions, and it has some indentation. At the beginning, we have a start. At the end, we have stop. And then we need to declare our variables. This is common in many programming languages, but not in Python. So declaring means that you specify the names for your variables, and the compiler will assign each of them a specific memory part, a specific part of the memory. In the next step, you just write the read instruction, but this doesn't respect the syntax of any programming languages, because you cannot simply do, you cannot write, for example, read ABC and imagine that some programming language would understand that, get this from the user and store them in the correct variables. This is just for us to know how the program will look like. Then after reading part, we have the condition. We want to compare if A is greater than B, similar to this here. And then you see in the several lines after the if, we have a part of code, a piece of code that depends on the results of this. So we indent them. So we have here another if, which corresponds basically to here. And then again, we indent once more, because this print operation depends on both if conditions here. But similar to the passes that we have here, and let me show you. So here we have two directions, true and false. Here in our if, we will have two directions. This corresponds to the true part. We will discuss them more and more. Don't worry. And this corresponds to the false pass. So this basically means that if A is not greater than B, then what would you do? And we have the printing operations at the end of these ifs. This else branch, for example, corresponds to this pass. So all these corresponds to this part, I think. And after all these printings, we remove the indentation that we have. We go back here and write stop, which means the program terminates here. So here we need to check our pseudocode. So it has all the variables, we have the reading, we have the printing of results. We are considering all possible cases. We need to check that we don't miss any case. For example, it might be that we remove this else part. When we are checking our pseudocode, we need to discover that it is missed. When we have a pseudocode, I mean, we don't need to have both pseudocode and flowchart. Usually we just continue with one of them. Actually, pseudocode is more common, I think, especially when you have larger programs. Writing their flowchart gets very big and very difficult to fit simply on paper. So we have seen the analysis phase, which was about thinking about the problem, thinking about the solution, representing our solution in a structured way, and thinking about input and output. This is the first phase, which is inevitable in any programming that you do. You cannot directly jump to the coding, otherwise you cannot succeed here, most likely. Then after this analysis comes the actual coding. In the coming slides, I will talk about coding, but I'm not yet going to introduce any specific programming language. I will talk about the notions and terms that are common in most of the high-level programming languages. Since you learn the logic, it's easier for you to continue to learn any programming language that you like. And in this course, we will continue in the next lecture with Python. So let's continue here. So now let's introduce the building blocks of programming and those things that are common in many programming languages. The first one I want to talk about is called the variable. Variable, as we already discussed, is a location in the memory that stores some temporary data which you are using in your program. And this data can be modified, can be written to, read from. And what is important about this variable is that you need to give it a unique name. So let's see an example here. Here we have some variable called x, and on the left-hand side, we have some instructions. Here we have an assignment instruction, which simply like what we do in mathematics, assigns this value being 10 to x. And here we have the flow of logic, that flow of time, that it is shown here by this arrow. So in this rectangle, it wants to give you an idea of the memory which is assigned to this variable and what value it contains. So after you do this assignment, the memory part will show value, will store value 10. And then imagine in your program later on, you have another assignment which assigns 20 to x. So this old value will be removed, and the new value will be written on it. So please have in mind that all these are referring to the same location in the memory, which is related to variable x. They are not different locations. And imagine in the next instruction, you want to assign x plus 1 to x. So again, this memory location will update its value by 21, and then comes the last operation, which multiplies x by 5. Each time an operation is going to be done, it will take the latest value. So for example, when we have x times 5 here, we are not going to use value 10. The compiler and the memory know that the latest value is going to be used, because the older values are already deleted. We don't have access to them unless we store them in some other variable. But otherwise, we don't have access to them, and the latest value is going to be used. Another common term is called the constant. The constant, as opposed to a variable, is a value which, as its name suggests, is constant during the execution of your program. There are some constants that are predefined in programming languages. For example, there is a constant for pi, but there are other constants that you can define. Imagine you have a program which wants to list the students in a class, and always you want to have the maximum number of students to be a specific value. For example, you don't want your classes to have more than 25 students, and you specify that constant, and every programming language has a way to differentiate between constants and variables. So a constant will remain constant, and you cannot change it by user variable or by user input or assignment, etc. So when we are working with variables, what is very important is that we know what are the data types of those variables, because variables can be different things. For example, a variable or a constant also can be numbers, and numbers can be integers and floating points. Programming languages care about the data types because it matters in their operations. In many programming languages, in most of them, basically, you need to specify the data type, because then based on the data type, they specify a certain amount of memory for your variable or your constant. But because some data types require more memory, some require less memory. But in Python, the data types need not be and will not be specified directly. The program interpreter is smart. It tries to discover the data type, and sometimes we'll see there are some conversions needed that it will do. But we need to get familiar with different data types. So for if we have numbers, we will have integer and floating point. We can also have booleans, as we discussed in the previous lecture. Booleans are simply true, false, or 1 and 0. They can usually be represented in both ways, either true or 1, and false or 0 can be considered the same thing. But these 0 and 1 are logical values. They are not like integer values. For example, 1 plus 1 in Booleans have a different meaning than 1 plus 1 in integer, because, for example, we don't have 2 in Booleans, so 1 plus 1 in Boolean will not be 2. The next data type I want to talk about is our characters. So characters are simply the input by your keyboard that you will have. And so it's just one single item. So as you see here, capital letters, small letters, or question mark, or exclamation mark, percentage, etc. Every single one of them is called a character. And between different characters, there need to be a space given by a space or comma or some sort of, if they are placed directly after one another, they are not considered as characters. They are rather considered as strings. So strings are a sequence of characters, and they can usually combine alphabetical letters with underscore and numbers, as you see here. But each programming language has certain rules on how you can build the strings. For example, most likely you are not allowed to put percentage or exclamation mark or question mark in your strings. And another data type which is very much used in the programming languages are called lists. Lists can be, for example, a list of grades of students, a list of geometrical shapes. It depends on your program and what you are trying to process. Imagine, for example, you get some grades as input, then you want to make a list out of them, and then, for example, you want to process that list to find the maximum, the minimum, the median, etc., etc. It's very handy to have lists as opposed to single variables. We will see in an example. So after variables and constants and data types, we arrive to statements. What are statements in a program? Let's first introduce syntax. Syntax is a set of rules that defines the structure of the language. You can think of syntax as the grammar that we have in human languages. For example, where should the verb be placed in a sentence? Where should the object be? Where should the subject be? How do we form questions in a language? How do we form imperative sentences in a language, etc., etc. We have similar rules in programming languages, and they are called syntax. A statement is one or several lines of code that is written according to the syntax of a programming language. Again, you can think of syntax as the grammar. And a statement expresses an action that needs to be carried out. It looks fancy, but it's actually very easy when we take a look at the examples. So we can have several statements in a program. Let's first consider a statement in an English language. Yeah. Here you see a statement in a programming language, for example, Python. So it gives an instruction to the program, and it is based on a specific syntax, which says, for example, you can use the keyword print, then you need to open and close parentheses. Then inside the parentheses, you need to use double quotations before and after your string. And then inside double quotations, what characters can you put and what things you cannot put. So although this seems a very simple statement, but it is still following a set of rules. So now let's see what kind of statements can we have. One which is very common is called the assignment statement, which is very similar to the assignment that we have in math. So on the left-hand side, you will have a variable name, then you will have equal character, and then you will have a value which is assigned. But the meaning of that is that the variable who has the name A will have the value 5 after executing this statement. The meaning is basically called the semantic. Each statement has a meaning. So semantic might look like a fancy name, but it's simply the meaning that a computer understands from the statement that you have written. And the semantics of the computer languages or programming languages can be different from language to other language, but they actually have a lot of similarities as well. So now let's see what are expressions, because in assignment statements, we might not have just this value, a very simple value here. We might have an expression. So expressions are a combination of values to create a new value. And they should again respect the syntax of the programming language. For example, imagine X and Y are two Boolean variables, then having X keyword, this is a keyword, imagine in some programming language. X and Y is a valid Boolean expression. Or having A star 2 plus 3 minus 1 is a valid numerical expression. Usually across all high-level languages, this kind of expression is valid, I think. But for example, this is not a valid numerical expression. When we write math, it is very common that we write A times 2 in this form. Use dots instead of X or asterisk. But this is not usually acceptable or valid in programming languages. We should show multiplication by asterisks. Now let's take a look at other types of statements. So we have seen so far assignment, and we have after assignment control flow statements, which as its name suggests, change or control the flow of the program. Think of the flow as the flow we had in the flow charts. So the assignment statement doesn't change the flow of the program like the very first flow chart that we saw. It keeps it as it was. It continues intuitively in a straight line, but there are some statements that can change the control flow of the flow of the program. They are called control flow statements. They are usually three groups. First one is called conditional, second one two loops, and the last one we want to introduce is called functions. All these logical meanings are used in almost all top-level programming language. It's very useful that you learn them, even if you are not going to work with Python, for example, later on. They will be handy in any programming language. So let's first talk about conditional statements. A conditional statement allows us to run a block of code sometimes and other blocks other times. And examples of it are if, else, and while. Let's see more clearly their syntax and semantics and examples. So, if statement, it's a semantic suggests that if the expression written to if is true, then do the code inside the block. Otherwise, don't do the code inside the block. they are very similar to the statements we use every day. For example, I say, if I am tired, then I get T. So this basically means that if this condition holds, I will do this operation. If this condition doesn't hold, I will not do this. This is similar when it comes to programming as well. So, and these words that I have written in a bigger font mean the words that are usually the keyword in any programming language, meaning that they will use specific words that cannot be used for other purposes. For example, if cannot be name of a variable because it is already reserved to show the if statement. And when you program, you need to take care of capital letters and small letters. It is always very important. For example, if with small I and small f cannot be name of any variable in your program, but if you change I and f to capital letter, you will most certainly use it as a variable because it's a different thing. So let's go back to its syntax. Its syntax, the syntax of if statement usually looks like this, but there are some differences from program to program. Here we are not discussing a syntax of a specific language. This is what usually programs have in common. So we have if keyword, then we have an expression that needs to be validated. For example, if A is greater than B. This is a simple expression. And then we have the keyword then, but in some programming languages, we don't have that. Then these dots here show a piece of code, a block of code, several lines of code that will be executed if expression holds. Then we might or might not have else keyword. You see it is indented, which means that it depends on the result of the if. So automatically, if the expression here is not correct and does not hold, we will be skipping over these lines and come here. And then the code inside here will be executed instead, not the one here. For example, I say, if I am tired, then I get T, else I will continue my work. Then so if I am not tired, the first part will not be executed and the second part after else will. And then after if and else, we might have in our programming language and if. We need to show when the if terminates. In different programming languages, there are different ways. In Python, it is something similar to this. We will see more details in the next lecture about it. But now we just want to see what examples show us to absorb the meaning of if statement. So we have an example here, which is taken from our previous example that finds the largest number among three numbers. So here I have written one of the if statements there. So if A is greater than B, then print A, else, which means that if A greater than B doesn't hold, which implicitly means A is smaller than or equal to B. Then it says print B, and after this part, and we have end if, which means that this block of code finishes. And you see we have indentation, we have one level of indentation here, we have two levels of indentation here to show that which statement depends on which part. So we introduced the conditional statements such as if, which we saw checks an expression, and if it is true, it will execute some part of code. But sometimes we need to check an expression over and over again and run the same code over and over again while this expression is true. For this purpose, while statements were introduced. Their meaning or their semantics is very simple. It says while the expression is true, loop through the code, not just run the code once, which is what if statements did. So here we will see how its syntax roughly looks, and we'll see also an example. So the syntax is usually something like this. So we have the while keyword, then we need to specify some expression for it. This the expressions are usually written using the variables in the program and maybe some constants, and they are like a small formula. So while this expression holds, then this code inside, which is indented here, will be executed. When it is executed once, we arrive here. This keyword, which is used in some languages, says, okay, now we are not done. Go to the beginning and check the expression again. So it comes here, checks the expression, and then if it holds again, it will execute. So this will continue until the expression doesn't hold anymore. When it doesn't hold, then it will jump over this piece of code and it will continue in the lines after the while block. This is called the while block because it is a block of code. Then after that, there might be some other lines of it. So if the expression doesn't hold, the execution of the program will continue after the while block. So let's see an example. So imagine we have a variable n to which 20 is assigned. Then we come to our while loop. We check whether or not n is greater than 0. In this case, when we start, 20 is greater than 0. So the expression is true. So we come inside the while loop. And okay, we need to follow these steps, then all of them need to be executed. So we assign n minus 2 to n. This is an assignment statement. After that, we have a print statement, which says print the new value, n. So you can imagine we will have 20 minus 2, which is 18, being stored in n. Then print n will print 80. So when we arrive here, it means go back to the beginning of while. It will not go before, it will just come to the expression. And evaluate the expression once more. So n is 18 at this point. Is 18 greater than 0? Yes, it is. So it comes and subtracts 2 from it. So n will be 16. And it will print 16 and so on and so forth. So what it will done is that it will print out positive even numbers under 20. When n is 2 is the last time that this expression will be executed. Then we will print 2, and when n is 0, we will print 0. And then when we come here and imagine n is 0, this condition will not hold anymore. So we will go and continue after the while loop. There might be some other expressions afterwards, or the program might terminate. It depends on the program. So now I want to introduce the very popular for loops. It's usually used in any program that you have. It is very common to be used in programming languages. So far, we have seen while loops, which were some sort of conditional loop that would run until the expression given to the while loop holds. Here we have for loops, which will execute the same block of code over and over again for different values. And they bear some similarity to while loops, but they also have some differences. Let's see how their syntax looks like roughly. So here you see in their syntax, usually they have the for keyword followed by some variable assigned to a start value. This is called the counter of the loop. For example, imagine you want to print something 20 times. So you want to have a counter which is first set to 1, and you want to finish when the counter is equal to 20. So you will have a start value, and then usually you need to have the keyword 2, and then you specify the end value. And then inside here, you need to write the code that needs to be executed each time. After the for loop, there is some way in any programming language to show that the for loop has finished now. For example, it can be called end. Let's see an example. So here we want to read 20 lines from a file. So we have for line equals to 1. Line here is called the counter of the loop. For line equals to 1, 2, up to 20. So it will consider line 1, 2, 3, 4, 5 until 20. For all these values, read a line from the file. This is the rest of this line. I should fix the indentation. Read a line from file grades.doc, and then the for loop finishes. So this for loop will simply repeat this operation for 20 times. This operation does not depend on the loop counter in this example, but usually inside the for loops, the operation that you do here depends on the counter. For example, you imagine you go to the, you say your program to write the line number specified in the counter. For example, first time you read line number 1, second time you read line number 2, and so on and so forth until you reach 20. When you reach 20, this for loop will terminate. But before that, each time this is executed, it will go from the beginning and check the counter. This counter will be incremented by the program, and you can have a control over it. For example, sometimes you want to increment it by 1, sometimes you want to increment it by 2, sometimes you want to decrement it. For example, you start from 20 and you decrement it each time. Then all this can be specified in the kind of programming language you're using, and the code will be executed accordingly, according to the counter, until it reaches the limit. So now let's talk about program blocks. There are several blocks in each program. Each block consists of one or more declarations and statements. For example, consider an if block. A block is something which is sort of independent from the rest of your code and is complete, means that it is not a broken statement, it is complete, it has a legitimate start, it has a legitimate end. For example, if you write just an if keyword without any expression and without any end, this is not a block because it is not a legitimate part of code. The blocks of code can be nested inside each other, meaning that they can be put inside each other. We can take a look again at the example we had before, in which a if block was inside another if block. So you see here, we have the outer if block, which is here, and inside it, we have another if and else blocks. And again, here inside the else, we have another if and else block. So this is called nesting. We could have, instead of if, a while statement here, and inside it, we could have an if block. So the statements can be nested inside each other. We just need to follow the syntax so that we don't mess up. A program that you write can consist of several parts, and there are several terms that are used in programming for program parts, and I want to introduce them now. The first one, that the most general one, is called subroutine. A subroutine is a point in the program that you can jump to from almost anywhere, and when you jump there, you can pass some arguments, and some computation done is basically in that part of the program, and you might have some return values or might not. Then the next term that I want to introduce, and we will talk about it in more detail in the coming slides, is called the function. The function is a special type of subroutine that returns a value. This is the key difference between a function and a procedure. A procedure is a subroutine that doesn't return any value. For example, imagine you can have a function that you give it several numbers and it returns the sum of those numbers. But a procedure, for example, can be a subroutine that you return to it some numbers, but it just prints out the sum of those numbers. It doesn't return any value. The key difference between function and subroutine is just returning or not returning any value. Functions are also called methods in programming. So what is a function? A function is a group of statements in the program that has a specific task. For example, imagine you have a function that computes the square root of a number. They bear some similarity to functions that we have in mathematics. Functions have their own, they have a name, they have a set of input arguments, and as we said, they return always some value. So instead of writing a large program like a big block of code, sequence of statements, what is more preferable is to divide your program into small functions so that each of them performs a specific task. It is very good that your functions are independent from each other and each of them are specialized in doing some task. And functions, as I said, can take input arguments, or you can also have functions that don't have any input arguments. And the functions always produce an answer value, or they return some value for you. They return, for example, the result of their computations. So let's see how their syntax really looks like. So as I said, they are a piece of code. They contain several statements, and we need to first have the function keyword. In some of the languages, in some they use func or other keywords. This doesn't matter. It's just something to check in your target programming language. But what is important is that there is usually a keyword that specifies now we have a function, and then you need to give a unique name to your function. It should not be, for example, name of any variables that you have already had. And then usually you specify your input arguments inside 2 parentheses. And then comes the code that will be executed inside the function. And you see here we have an indentation to show that this piece of code depends on the function. It's not just a standalone code in your program. It will be only executed after you enter this function. And at the end of the code of a function is a special line of code which returns some calculated value. This value is usually defined inside the code here. So let's see an example. So here we have a function which we declare it here. This is the function keyword. It is always needed to be there. Then comes the name that we choose. This function keyword is nothing that we choose. It is specified by the programming language. It is a rule that we need to follow. It is a syntax that we need to follow. But this name that comes afterwards is something we choose. But again, it should respect some rules. For example, it needs to be a certain set of characters just follow each other. They cannot be, for example, a space between them, etc. You can check it in the language you want to program. And then here we have parentheses to specify the input arguments, and we have two input arguments, base and exp. And if we want to compute the exponential like this, so here we have the result, which is the result of the computation. We have chosen this name for it. It is good that the names of the variables and the functions that are in your program are meaningful and are very close to what they are doing. So here the result is first 1, and then you see here our algorithm says start from 1 to exp, which was given as an input argument. So we will have a for loop here going from 1 to exp, and each time our result will be multiplied by base. For example, if you want to calculate 2 to the power of 3, your result will be first 1, then each time you will multiply the current result with 2. So first time you get 2 as a result, second time you get 4, and third time you get 8. And then the for loop finishes because you have reached exp. So you come out of this for loop. I have missed to put the end for the for block. There usually should be some sort of end here. And then the value that is computed should be returned. So here the result is returned. So in your code, whenever you want to use this function, it is called calling the function. In programming, it is usually called calling the function. So imagine we have a variable a, we want to call the function exponent to compute 2 to the power of 3. So this time we don't need to write the keyword function anymore. This definition exists somewhere in our program, but when we want to use it, we just use its name, which we decided it to have. So we just use its name and we pass to it the input arguments. You see, we pass them as explicit values, or we can pass other variables. We don't need to write these names here when we call the function. These are just for definition of the function. These are just for the function to know how to use the input variables. So in order to do that, it has to know some unique name and needs to relate them using these unique names. But when we call a function, we don't use these names. We just pass the values, and the results will be returned automatically after the function finishes, and they will be stored in A. So after this, executing this line, A will be actually equal to 2 to the third, or it will be essentially equal to 8. And here we have another example for calling this function. We have a variable called ABC, which we want to store the result of this 3 to the power of 10. So again, we call the function, we just simply pass to it these values and it returns. You see, if we didn't have the notion of functions, each time we needed to calculate exponentiation, we needed to repeat all these lines of code. This is not very readable. This will make our programs so big and difficult to follow. Functions are really a bless to make clean programs and divide the work to smaller pieces and make the things that are repeatable just repeat once, and then we can use them over and over again by the function, by calling the function. So let's see a bit in more detail why we use the functions. So as I said, we need them to break up the programs and algorithms into smaller and more manageable pieces. Always remember this, when you have a long code, it is difficult to manage it. It is difficult to update it and fix the problems and bugs in it. It is always preferable to find a way to write the smaller programs or divide your program into smaller chunks. So functions make it easy to write and test and debug programs. The term debugging, if you remember from the first lecture, was first used by Grace Hopper because in their computer, which was very modern at the time, a bug simply went inside the electronic parts and made the program and the computer not work properly. The same term has been used since then, and whenever we have a problem in our program, we say we have a bug, although it's not a real bug. And whenever we want to solve that problem, we say we are debugging. If you work in a team of programmers, it's usually easy to divide the work by dividing the program to several functions, and each member is responsible for a specific function or several functions. And having functions in your program increases the reusability. It means that you can have the same piece of code that is used over and over again without needing to write the instructions over and over again. You just simply call the function. So it avoids simply repetition of code. So bingo, we have covered analysis of the problem, and we have also covered coding and what are the popular kind of statements used in simply all high-level programming languages. Now imagine we have analyzed our problem and we have come up with an algorithm and we wrote our pseudocode, and then based on our pseudocode we have written our program. Now what remains to do is to test our program. It is never enough to just write your program. Almost every time you need to test your program, even if you are a very experienced programmer. So in testing, you simply need to try to see if there are problems in your code. And the way to do that is usually by using test cases. Test cases are simply specific input and expected output. For example, when you imagine you have a function that just imagine your program consists of just function which calculates exponents, as we saw earlier in these slides. Then a test case would be specific inputs. For example, 2 as the first argument, 3 as the second argument, and the output you expect to do and is correct would be 8. Then you try this test case on your program. You pass the inputs to that and see whether or not you give the expected result. If you do, bingo, you continue to the next test case. You need to define several test cases for your program based on the behavior you expect it to do, because what you program is not always what you expect. And when it comes to testing, it is always important to try as many cases as possible. Try the difficult cases. For example, try negative numbers, try 0, try give faulty inputs, see how your program behaves, and then improve your program based on the results of the test. If you see that some test case suggest some output, but your program gives you another output. You need to then go back to your code and see what parts in your code are not doing as they should. What is the problem? Maybe, for example, you have an expression which is faulty. Maybe somewhere you are doing addition instead of multiplication. Maybe sometimes you have forgotten some piece of algorithm. Simply you dropped some piece of the sequence of instructions, etc., etc. So each time you need to go back to your code, fix it, and try it again and again. So thank you for your attention. This was our lecture about basics of programming, in which we covered what are the terminology used in programming, what are the steps toward programming your program, and what are the common statements that there are in typically any high-level programming language. Please feel free to ask your questions on forum, on Studium, or email us via Studium. I will quickly show you in case some of you might not be familiar. So when you see here in the discussions, you can always create a new discussion and ask your question. And also for emailing us, you can use this function. And then you can create a new email here. And first you need to choose the course. And then you can choose to whom you want to email. For example, being the student or, the teacher or teaching assistant. And then this will reach us and we will answer you. And we are also arranging the open Zoom sessions. The schedule is on the course calendar on Studio. And I have already sent you a link to a doodle poll to see which times fits you better for these sessions. I know that some of you are working, so in case you prefer evening time or weekends, please just fill in the doodle so that we know and we can plan as best as we can to fulfill your needs. Thank you once again and good luck.